Okay guys, welcome to this video. It's on Chemistry 102, Week 6, Lecture 1, but it's only going to focus on the beginning of this lecture on Chapter 14, Section 5, which is based on determining the direction of a reaction, and we're going to use what we call the reaction quotient Q for that. Alright, so basically what it is the reaction quotient Q can predict the direction of a reaction. So we look at it, and what it says is the reaction quotient Q can predict the direction of a reaction when you have A and B, and then your reversible to give you C and D. What that says is your reversible. That it says that it's in dynamic equilibrium. So Kc, you can see your Kc value is your concentration of your products or your reactants. It's the same, but Q is all, it looks the same. It is this concentration of products over reactants, but it's not the equilibrium concentration. It's just the regular molarity, molar concentration. So Q looks identical to your Kc value, but the concentrations are different, and also Q is going to be changing a lot, whereas Kc is a constant. So that's never going to change. And when they equal each other, then you know that you are at equilibrium. Okay? So, predicting the direction of reaction. How do you know, what direction? Are we going in the forward? Are we going in the reverse direction? Well, we got to determine that. We have to figure out what Q is. We're going to know what Kc is. Alright, we're going to know what Kc is. It's going to stay constant. So if your Kc equals 1, it's going to stay at 1 as long as the temperature isn't changed, as long as that remains constant. Now, your Q value is going to be your products of the reactants, but it's not going to be the equilibrium concentrations, and this is going to change as a reaction moves towards equilibrium, because that's the goal of every reaction. It's to move towards equilibrium. So when Q is less than K, is less than Kc, your reaction is going to, well, which way does it go? Well, we can draw it out. The thing is, we can draw it out. So when you draw out the number line, alright, so this value right here is going to be Kc. Where Kc is the point of equilibrium. But if Q is less than that, Q is over here, then it's not equilibrium. How do you make it at equilibrium? You have to make them equal each other. How do you do that? Well, Q is constant. It cannot be changed. But I'm sorry, K is constant. It cannot be changed. But Q can. So we can move Q in the forward direction here. And when we this is essentially what we're doing here, is we're increasing Q. We're increasing the concentration of Q so we can move to the right. Or a lot of people like to say the forward reaction. And what you do, let me just make some room here. What we're doing here, okay, what we're doing here is we're increasing, let's see here, alright, we're increasing, so if this is K, it's really Kc, but whatever, I'll put the C right there, and Q's here. If we increase Q, we're going this way, so we're moving in the forward direction to the right, and then here's the equilibrium, and we're good. You can think of this as an equation where you know that your reactants are going to be on the left side, and your products are always on the right. So make Q be the double arrows, which it truly is. That's what it is. Like Q represents this. So we can correlate that to the reactants being on the left side, and the products being on the left, being on the right side. I'm sorry. The reactants are on the left, products on the right. So because of that, if we have to increase Q to get to, what's that mean? Well, if the reactants are on the left and the products on the right, and Q is less than Kc, that means Q is on the left side of Kc, which means Q is favoring the reactants, which means there are currently more reactants than products right now. But we don't want that. So when we increase the Q, we are effectively decreasing the reactions. And then as an effect, we are increasing the products from a lesser value to a higher value, so we can get that equilibrium going. And then the opposite is what happens when Kc is greater than Kc. So when Q, right? So here's K, C, and Q is going to be over here now. It's greater. When Q is greater, you have to go to the left. When you go to the left, you're going in the reverse, or to the left. A lot of people like to say. So we are decreasing Q, which means we are decreasing our products and increasing our reactants. Because currently, if Q stays over here, there are more products than reactants, so it's product favored right now. But it's not an equilibrium. So we got it over here to get the equilibrium stage right there, and then decrease the products to give us an increase in the concentration of reactants, and that's how you do it. Here's a representation of it. When Q, you can see, is equal to Kc, they're equal values, and thus we are at equilibrium. Okay? Q equals Kc. If you notice here, Kc is the same value each time. It doesn't change, again, because it's constant. It will not change. The Q will, though. The Q's will change, right? The Q's will change. And here you can see that the Q is less than K, thus we got to increase it going to the right. And then here the Q is greater than K, so we got to decrease it by going to the left. Again, over here, you have more products, and over here you have more reactants. But we don't want that. We want equal amounts, or we want equal rates. So Q, so we can get the Q equal to the Kc. Here's another representation of it, which I really like. And here we have 0. Q is 0. So here Q is 0, and up here Q is like, right here Q is what? So it's like a little bit over 3.5. We'll just say around 3.5. So here's your products, and here's the reactants down here. And why? How do we know that? Well, look at this right here. It says K equals 1.45, and it's pointing to this red line. So that red line's our equilibrium point. Is where it reaches our equilibrium, so K equals Q. So down here, we need to increase the K, or I'm sorry, the Q, to move it up here. And then on the other side, we need to decrease our Q to get it to our equilibrium point. So this is just another representation of it, and I like this because it just helps to visualize how everything works, and there's a lot of different relationships, and hopefully that can help you a little bit.